Welcome, curious minds, to another deep dive. Today we're embarking on a truly monumental journey, exploring what many scientists call the second most important equation in all of science, sitting right there alongside Einstein's EMC2.
That's quite a claim, isn't it?
It really is. And this isn't just a formula. It's a profound thought experiment, a roadmap, if you will, to the most ancient and pressing question humanity has ever dared to ask. Are we truly alone in the universe?
It's fascinating, isn't it? Because the power of this equation, the Drake equation, isn't found in giving you a definitive numerical answer, which, as you'll discover, it famously cannot.
Right.
Its true genius lies in forcing us, the scientific community, and indeed anyone who ponders this question, to systematically grapple with the immense, often humbling uncertainties involved in the search for life beyond Earth. It organizes our ignorance into inquiry.
That's a powerful way to put it, organizing ignorance. It truly is a remarkable intellectual tool, and it was famously sketched out by Dr. Frank Drake back in 1961. This wasn't some grand academic project. It happened at the very first scientific meeting dedicated to the search for extraterrestrial intelligence, or SETI, held at the National Radio Astronomy Observatory in Green Bank, West Virginia.
Right, Green Bank.
Drake didn't invent it to crunch a precise number right then and there. As our source material beautifully illustrates, it was designed as a roadmap for astrobiology, a starting point.
And that really is key to understanding its enduring legacy. Drake's intention was not for purposes of quantifying the number of civilizations, but as a way to stimulate scientific dialogue.
Okay.
Before he put pen to paper, discussions about alien life were, as former NASA Ames scientist William Barucki vividly described them, vague speculations. The Drake equation changed that completely.
How so?
Well, it provided a structured framework, a conceptual flagpole around which people can debate their science and attitudes, unifying disparate fields of research from Martian geology and the mysteries of abiogenesis to the intricate high-tech searches for alien signals we conduct today.
A flagpole for debate. I love that imagery. It's essentially a logical cascade, isn't it?
Exactly.
You start incredibly broad with the sheer vastness of the cosmos, then you progressively narrow your focus. You move from factors that are relatively well understood and astronomically quantifiable.
Things we know more about now.
Right, things we've made incredible strides in understanding thanks to groundbreaking missions like Kepler and TESS. But then, almost inevitably, you step into the biologically speculative, where we're largely dealing with a daunting sample size of one.
Our own Earth. Yeah.
Our own Earth. And finally, you land squarely in the sociologically enigmatic, which is almost pure conjecture about alien psychology, choices, and their ultimate fate.
It's an ingenious way of taking an overwhelming, almost spiritual question and breaking it down into manageable, testable, albeit still incredibly challenging parts. It maps out the scientific journey for future discovery.
So the equation itself.
It's often written as NAIE, FP, FB, and AAA, FLE, Phi, AFC, AL. And as you hinted, each variable peels back another layer of this grand cosmic mystery.
Okay, let's unpack those variables quickly for everyone listening, because understanding what each stands for is crucial to appreciating the equation's depth. N is the number of detectable communicative civilizations right now in our Milky Way galaxy.
Whose signals we could potentially pick up.
Exactly. Whose electromagnetic emissions, think radio waves or other signals, are out there for us to potentially pick up.
Okay.
Then we have R, which stands for the rate of formation of suitable stars in our galaxy, effectively. How many stellar cradles are being born each year?
Right. Stars like our sun, potentially.
Potentially. Then FP is the fraction of those suitable stars that actually have planetary systems orbiting them.
How many stars have planets, basically?
Yeah. And F is the average number of planets per star system that have an environment suitable for life, what we often call the Goldilocks zone.
Not too hot, not too cold, just right for liquid water.
Precisely. Now we transition into the biological unknowns. Flay is the fraction of those suitable planets where life actually appeared.
The big one, abiogenesis.
Where abiogenesis, the spontaneous generation of life from non-living matter, actually takes hold. Then Phi is the fraction of life-bearing planets where intelligent life emerges. And here, intelligent specifically means capable of developing technology.
Tech-capable intelligence, that's key.
Very key. And finally, the sociological factors. FC is the fraction of those intelligent civilizations that develop technology advanced enough to release detectable signs of their existence into space, like powerful radio broadcasts.
Whether they choose to or happen to signal.
Right. And L, perhaps the most profoundly impactful variable, is the average length of time such communicative civilizations produce those detectable signs, essentially,
Yeah.
how long they stay on air.
It's a testament to how science takes something that feels almost too big to comprehend, too overwhelming, and provides a precise language for its exploration. It helps us understand not just what we know, but precisely what we don't know.
So with Drake's roadmap laid out, let's begin our journey at the very beginning of the cosmic story, the ultimate real estate market of the universe, the cosmic nursery.
Okay, sounds good.
It's incredible to think that back in 1961, when Frank Drake first scribbled this formula, the first three variables, R, F, P, and Ni, were almost entirely guesswork.
Total guesswork.
I mean, we had very little concrete evidence of planets outside our own solar system.
That's a crucial point. It was a monumental leap of faith for those early SETI pioneers. But fast forward a few decades, and we've experienced what can only be described as a seismic exoplanet revolution.
A revolution indeed.
Missions like the Hubble Space Telescope, and especially NASA's Kepler and TESS missions, have truly transformed these initial variables from mere conjecture into robust, data-driven estimates. It's one of the most exciting shifts in modern astronomy.
And that's exactly why this part of the equation has become so much clearer. The biggest uncertainties in the Drake equation are no longer about whether there's enough cosmic real estate out there for life to emerge.
We kind of know the answer to that now.
That question, happily, seems to have been answered with a resounding yes. Now, the truly elusive questions have moved squarely into the realms of biology and sociology.
Let's start with R, the rate of star formation. This is the galactic forge, the engine setting the foundational pace for new opportunities for life across the Milky Way.
Okay, the star birth rate.
In 1961, estimates for R were broad, ranging from a conservative 1 star per year to a more optimistic 10 stars annually. It was largely a best guess.
But modern astronomy has really powerfully refined that. Instead of just counting individual stars, we now measure the total mass of gas condensing into stars annually across the galaxy.
That's a much better approach.
Recent data from NASA and the European Space Agency, particularly refined by the ESA's Herschel Space Observatory, suggests our galaxy produces about 1 to 2 times the mass of our sun in new stars each year.
So about 1 to 2 solar masses per year. And that's a significant refinement because it tells us about the sheer volume of new stellar nurseries. It's important to clarify that a rate of 1 to 2 solar masses per year doesn't mean just 1 or 2 sun-like stars are forming.
Right, because most stars are smaller.
Exactly. The vast majority of stars that form are actually low-mass red dwarfs. So that 1 to 2 solar masses per year translates to the birth of roughly 6 to 7 new stars annually on average.
6 or 7 new stars every year.
The key insight here is that the galaxy is consistently, steadily producing a bountiful supply of potential stellar cradles.
And it's been doing it for an incredibly long time. Our own Milky Way, believe it or not, experienced a stellar baby boom about 10 billion years ago,
Way back then.
churning out stars about 30 times faster than it does today. Our sun, which formed around 5 billion years ago, is actually a relative latecomer to this cosmic party.
We missed the peak.
We did. Born when the galaxy's star-birthing frenzy had already slowed to more of a trickle.
This cosmic history is incredibly vital for the Drake equation. It implies that conditions suitable for life could have been present around countless stars billions of years before our solar system even existed. Think about the implications. That's ample time for other civilizations to arise, evolve, flourish, and perhaps even disappear, long before our Earth even coalesced from stardust.
Billions of years of prior opportunity. But not all stars are created equal when it comes to hosting life, right? We're looking for suitable stars.
That's right, stars that offer the stability and longevity necessary for complex life to emerge and evolve. Massive O and B type stars, for instance, they burn out too fast.
Millions of years, not billions.
Yeah, almost certainly far too short a time frame for complex life to get going. Our sun, a G-type star, along with F and K types, are considered the most promising, offering stable lifespans of billions of years.
And those make up, what, 5–10%?
About 5% to 10% of the stars in the Milky Way. Then you have the red dwarfs, or M-type stars, which are incredibly common, making up about 75% of the entire stellar population.
75%.
They can burn for trillions of years, which sounds absolutely ideal for life to take its time evolving. However, their habitable zones are very close to the star,
Leading to problems.
leading to challenges like tidal locking, where one side of a planet perpetually faces the star, creating extreme temperature differentials. They also emit intense X-ray and ultraviolet flares.
Bad for atmospheres, bad for life.
Could strip away atmospheres or irradiate nascent life.